And this Hangout is live. Hey, everybody, this is Smitty Halibut from Twitter and various other places. I'm going to be building something tonight. I'm going to be putting together a schematic for a Learn to Solder kit that I'm going to be building and taking to a hardware hacking village that I'm running at a work event at the end of March for my day job. So it's going to be a little Arduino compatible, something or other. Probably going to have some 2812 WS2812 RGB LEDs on it. Maybe an IR transmitter and receiver, and like a ICSP header to program the thing. It'll be based on the ATmega 328, which is the same chip that's used on like the Arduino Uno platform, and maybe a few other miscellaneous headers. It'll be, you know, battery powered, that kind of stuff. It'll be very similar to the Learn to Solder kits that some of you may have seen at DEF CON in the last few years. I helped Crux design that kit originally, and I'm going to be doing something very similar. The software on it will be different. We're not going to be I'm not going to be running a full daemon at my work event. So the crypto little badge exchange that happens on the darknet badges doesn't really make sense here because we don't have the daemon on the back end to run it. So but I'm thinking of making the little IR transmitter receiver so that most people's badges are going to be healthy, but occasionally one or two people will come down with a disease, with a virus or something, and the IR transmitter will, you know, kind of spread this virus as you walk around and meet people, and so you'll be able to see other people's badges change color when they get infected, and then maybe I'll make a couple of badges that are like vaccines or some sort of cure for the virus. So if somebody gets the virus, then they go hunt down somebody who has the vaccine for the vaccine badge, and then like maybe the blinking of the virus LED will tell you how many generations old your virus is, and we'll see if we can get it completely eradicated by the end of the weekend or something. I don't know. I'm just making stuff up at this point, but that's kind of where I'm headed with it. Some sort of a badge that people will wear that has an IR transmitter and receiver on it, and we'll be able to code something up. So that's what I'm going to be doing tonight. Thanks for joining me, and be sure and join the Hangout if you have any questions. I'd love to chat with people while I'm doing the work and answer questions, and I will try and do kind of a stream of consciousness thought about what it is that I'm doing. I'm primarily working here. This is not going to be your typical YouTube video where I'm going to edit it and show and talk about things. It's not very well produced. It's not very well organized. This is just me sitting down in front of KiCad, trying to put something together. And I decided to start streaming it because I kind of like the idea of doing these interactively. I would love for people to join the Hangouts and ask me questions and talk to me and you know, make suggestions or whatever. Just shoot the poop, right? So come join me on the Hangouts. Right now, I need to go get KiCad open. Yeah. I don't know. Adam Baldwin asks, dude, do you even Z-modem? Not sure I do. All right, so that monitor is where I'm going to put the Hangout. This monitor is where I'm going to put work. That monitor too. Okay. And then do screen share. It's going to be weird, kind of me popping around from application to application. Unfortunately, I've got so many monitors. Wow, that's just straight up black, isn't it? Why is that? That doesn't look good. You can see my cursor, but you can't actually see the screen. Well, that's a bummer. New project. Create folder. Virus. Fine. All right. Oh, now it comes up. Just in time for me to pick a different, for me to pick a different screen. There we go. Ah, the blank sheet of paper. This is KiCad. A lot of people also use Eagle for their schematic designs. I used to use Eagle. I like Eagle. But a friend of mine, Nick, Exploding Lemur, kind of gave me a hard time at one point about using uh, non open source software. And so I tried using KiCad a long time ago, and it did nothing but keep crashing and losing all of the data I was working on. So I gave up on KiCad at that point. And then with 4.0, the recent general release of 4.0, KiCad has gotten a lot better, and so I'm giving it a try again. And I've been pretty happy with it. There are some things that it does differently than the way I would do it if I were choosing, or if I were um, that I'm used to. But all things considered, it's a pretty good system. And there are good documents on how to um, export files for use at OshPark. By the way, if you do circuit design or builds or anything like that, and you haven't heard of OshPark, do not pass go, do not collect $200. Go straight to OshPark and learn about their product, because it is pretty darn awesome. And I am a big fan of OshPark. I've been using them for a lot of my projects lately. I used to use ExpressPCB, and then I heard about OshPark, and I have not looked back. Where is it? Ground. There we go. So I plopped down my CPU. Everything's going to revolve around the CPU. And the first thing I run into my CPU are all my power grounds, or my power signals. What am I going to do? Well, I'm going to want a 2x3 pin connector for an ICSP header. And unfortunately, when I screen share just one window, it doesn't show the pop-up windows, the modals that that KiCad uses for things. So, for example, right now I'm actually working on, where is it? That screen. Nope, not that one. Just kidding. Totally lied. It's not even up here. Oh, that's interesting. So not only does it not show the modals, but since they're modals, they don't actually show up in the Google Hangouts share your screen selector thingy. Interesting. All right. Well, I'm not going to be able to show you what I'm doing right now then. I apologize. Trust me, though, it's terribly interesting. And I'm selecting connectors from a list of components. So that's going to be my ICSP header. And then I want to do probably a 1x6 for an FTDI serial port header as well. These are all pretty standard connectors that I add on all of my microcontroller projects. So since I want to make this an Arduino compatible, you need to have a serial port. Most Arduinos have a serial to USB converter. I'm not going to be putting a serial to USB converter on here, but because a lot of people have the FTDI 6-pin FTDI cables, and in the USB to serial chips are all surface mount. I'm going to try and keep this completely through hole. But so if I put the 6-pin header there, then you can just plug your FTDI connector straight onto it. Excuse me. The 2x3 up here for the ICSP is a very standard 6-pin connector that's used for the Atmel series of chips for programming it. That will allow you to program the chip like down at the brainstem level. Grab the flash starting at byte 0 and just load a new thing on there. For an Arduino setup, it's primarily used for if you need to reload the bootloader onto the chip for whatever reason. That's how you do it. Normally, once the bootloader's on there and you want to just upload using Arduino, you'll just go through the serial header if you've got the serial cable. But I'm going to be preloading these things with my own software, so it's not critical for the people who are learning to solder. But if they want to use this as an Arduino after the fact and hack on it, then they'll be able to do that. Okay. So what other hardware do I want? Well, I think I want a couple of WS2812s. I think I already created. Oop, I did not. Okay. I'm going to hold off on that for a second. Let's find my crystal oscillator. Yeah. No? Dang it. Resonator. That's what I call it. Or not. Dadgummit. You can see what I'm doing, so that's always fun. Oh, because I created a new project and I haven't imported my libraries yet. All right, I can fix that. Component libraries. Mm-hmm. Um, stand by. Oops, no. Apps. KiCad. Library is pretty. What the heck? Oh, hey, I can never remember how to do this. I can see my libraries, but I don't remember how to import them. Files contribute. Yeah, even the windows don't show up on. Seriously? Come on, G+, get with the program. The Hangouts. Tools, library browser. User shared library KiCad. No, that's not what I want. I want. Oh, this is glamorous, isn't this? There we go. All right. Okay. All right, let's try this again. And again, you guys can't see any of this, so I apologize. But that's the important part. Right there. Crystal resonator. Where does that go? Crystal. Okay. We'll rotate that like that. Somewhere. Okay, let's draw some lines. So this is a crystal resonator, which has its the bypass caps that are, they're not bypass. I don't remember exactly what they're called, but they're kind of loading caps for this crystal resonator. It's all a single component. It's a single 3-pin component that has everything built in for it, and it's kind of convenient because you don't have to select your capacitors, and it's one less thing to have to solder into the board, which is kind of neat. I am not going to go over how to use KiCad. There are plenty of other YouTube videos, I'm sure, that talk about that sort of thing. And that's not really what I intend this to be. So you might see me using some shortcuts or something, but I'm not going to be talking about that. There are plenty of other YouTube videos talking about how to use KiCad. Excuse me. Um, hmm. I have a new notification. Do I even zoom in? Okay. Let me tweet really quickly that I got it working. Yay! My Hangout is live. Come hang out with me, so I'm not just talking to myself. And then what is the URL for this hangout? There it is. And paste. Okay. Sorry for that little distraction. Okay. Um. What else do I need? I need a battery. So let's put a battery on here. Look, a battery. Okay. I'm going to want to diode mix that battery with the power that you get from these connectors so that we are not going to burn anything out. Diode, Schottky small. There we go. All right, we'll put that there. Move that up there. Draw that line from there to there. And let's see here. Just going to copy that ground to there. And I'm going to copy that VCC to there. And connect that. All right. So next thing, I need to go remember what the pin is for an ICSP header. ICSP header pin out. Oh, the Googles make this so much easier. Okay. So we're going to come over here. That is pointing to the right. Pin 1 is miso. Pin 3 is suk. Clock. And this is reset. Left this time. This one, oh, hey, okay. Mossy. So miso and mossy, whoops. Miso and mossy are terms like master in, slave out, and master out, slave in. So that's basically a transmit receive, but it's unambiguous as to who is transmitting and who's receiving at any given time. SCK is the system clock or the serial clock that is used to tell each other when a bit is being sent or when to send a bit. And then reset is just what it sounds like. It throws the CPU into reset, and then VCC and ground are exactly what they sound like. And those are enough pins to be able to program your Arduino. Set the value on this and make that CSP. Okay. Similarly, let's go do a pinout for FTEI serial pinout. There we go. And judging. Okay. So you'll notice that I'm not actually running wires to these things. I am instead putting putting labels on them, and then I'm going to run the labels to where I want them to be later. Also, I can put another label somewhere else, some other place, and without having to drag wires all over my schematic. I am much more a fan of labeling things and putting things into individual groups rather than trying to just have it all on a single schematic and drawing wires everywhere, which is impossible to read in my opinion. CTS and TX F So that's transmit from FPI. We'll call this FRX. And this one is RTS. We're actually going to use RTS and CTS, although I think RTS goes through a capacitor in series and then gets tied to reset, so that when you drive RTS low, if you put a big enough value of capacitor there, it will actually pull reset low for a little bit, and then the pull up on reset will charge up that capacitor, and eventually it'll go back high again. So by pulling RTS low, you end up resetting the CPU, which is used for Arduino programming. Okay. So I've got those. Oh, whoops. Apparently I moved that. I didn't copy it. Let's put that back. Oh, hey, haha. Nope. We're going to move that. Let's move that somewhere else because we need diode in there. And then similarly here. You know what? Delete that and delete that. Facing to the left. In. It's somewhat unlikely that you are going to use the ICSP and the FTDI serial cable at the same time on different voltage sources. So I am okay putting those into the same diode. There's got to be a better way to do this. Cleaner way of drawing this. Where? Okay, so then let's move that down there. Then I'm going to move that up there, but I'm going to rotate it. Put that right there. I'm going to move that there. And then here, I'm going to do left facing, and I'm going to make that in. Okay. Oh, try it again. So VN goes to that diode goes to VCC. VCC also goes to that diode, and that diode to that battery. I can get rid of that. I do, however, need one of those there. Okay. So we've got the battery going through a Schottky diode to VCC, so that if there's power coming in from VN, because that's likely to be 5 volts, you got 5 volts coming in there, that will pass through that diode, no problem, to VCC and power your circuit, but it will not go backwards into your battery, which is only going to be 4.5 volts. So what I'm trying to do is prevent this from powering this or this from powering that. We want either of those to be able to power the circuit without having to turn one off before turning the other on, but without actually feeding back power into each other. So that'll get the job done. It's just don't care. Hey. Okay, move you over there. That's fine. Okay. So that's our power input. While I'm here doing powery type things, let's drag that. Oh, no. Okay. Forget it. Hey. Ooh. I'm actually dragging. Okay. What key did I press to do that? I don't know. All right. So let's put some capacitance on here. These CPUs need some bypass caps. You can't just run VCC into them because they'll reset all over the place. So you throw some 0.1 microfarads or 1 microfarad caps on there on the power line, and that cleans it out. And you need to get those caps as close to the chip as possible. That's a layout thing. Right now, for the circuit, I can just put those right here. We'll do that. Value 1 farad. And need a few of these. I think there's only 1 or 2 for the processor itself. I think having one by the IR receiver, if I remember correctly, was also a good thing. So, whoop, hey, copy another one of those. There-ish. Okay. VCC. Eight. These will be physically placed closer to their components that they're actually bypassing when we get to that point. But for right now, we'll just do it that way. Okay. So I got my CPU on there. I've got the ICSP header. I've got the serial header. I've got my power section. The darknet badges. Let's see if I can find a picture of this for you. Darknet badge. Oh. Hang on. Hi, it's me again. So the darknet badge is something that I've been involved in making, and we got a whole images section on Google. That's pretty. Whoa, that's a lot of cool stuff. Wow, did I do all of that? Hey, look, it's oh crikey, why can't I remember his name? He's the guy who won the darknet 2 years ago and got a black badge, got an Uber badge out of it. Pretty cool, huh? That is an old design. Wow. Okay. So what do I need to obey? Neat stuff. Okay, so that's got a good picture of it. So this is our darknet badge that we did last year, and here's where the main CPU is. But you'll also notice there are these rows of pins right on the outside of it. They are literally just directly connected across, and those are there for putting female headers in or male headers if you wanted to be able to hack the thing after the fact. So this is actually very similar to what we're going to be building. There are the bypass caps I was talking about. This is a single package that has 2 diodes in it, but I found diodes that are cheaper than that. So we're just going to do 2 separate diodes on ours. Here's the FTDI serial header. Here's the ICSP programming header. Here's the crystal resonator, the 3-pin package that has the crystal and the capacitors in it. Here's the IR receiver, IR transmitter, and just a green LED that's used for talking to the users. This is very similar to what we're laying out here, although not exactly. Man, this is kind of cool. I wonder if this is Jeff's page or Crux's page. Oh, hey, look, a little breadboard and the display board. Man, we did some cool stuff. Crux gets all the credit for that. When I say we, I don't mean we, I mean Crux. That's my picture. So, okay, we're going to take a small tangent here. So last year at DEF CON, or actually this was 2 years ago. This was at the Riviera. This is not at Bally's. Not Rio. 2 years ago at the Darknet, we had quite the demand for our badges. And this is Sunday morning. I'm headed toward the Hardware Hacking Village, which is right through these doors right here. Sunday morning, and there is this huge crowd of people collected outside of the Hardware Hacking Village. Mind you, security is over here. They're not supposed to be here yet, but somehow they managed to get by. And they're all waiting outside the Hardware Hacking Village for the doors to open so they can come and get their badges. And I'm walking down the hallway with a dolly and a bunch of boxes full of all of these kits that these people are waiting for. And I turn the corner back here and I see this crowd and I just about lose it. And I saw that and I took a picture of it. And because I couldn't believe it myself, I'm like, okay, all these people are waiting for the badge that we're doing. And I went up and I asked them, like, what are you guys waiting for? And they're like, the Darknet badge. I'm like, oh, that sounds pretty cool. And I turned around and I walked this way to get into the Hardware Hacking Village through a different door because I couldn't very well just push all of these boxes with these kits right through this mob of people who were looking for stuff. So that was kind of fun. We had a good time with that. More pictures of our badge. There's one that's completed on the lanyards. These were some cool little keys, little projects that Spetku put together that she just did on her own initiative. There's a little 328 microcontroller there, some programming headers there, and a bunch of LEDs all over the place. And it just blinks and does some cool stuff. She gave me one of those. I feel very honored. That one's really cool. One, I don't know if that's serial number one, if that's something that Crux put together or what that is, but there's one hooked up to a logic analyzer. That's kind of neat. Yeah, we had some good times. Oh, there's a whole fleet of them on the panelized over at Osh Park. That is 21, no, 20, DEF CON 20, 20's artwork, because that's the smaller badge. That's the smaller one. And a whole bunch of them on a panel. Well, thank you for going down memory lane with me. Time to get back to some work here. That's not me, is it? No, that's not me. Okay. Anyway, time to get back to some layout work. Sorry for that trip down memory lane. Oh, what are we going to share? Let's share that one. So anyway, you saw those pin headers, and I am going to create those pin headers on this badge as well. So this is a 28 pin chip, and so it's going to be 14 pin headers down each side. Connections, go into con. I want a 1x14. And I want one there, and we'll go ahead and put one there as well. Okay. So actually, you know what? I'm going to move these up here. And you know what? I'm going to get rid of that, move this down here as well. We will use headers for the, or labels for those as well. Okay, now you'll notice that this chip is not laid out in the schematic in numeric order. So I'm going to put a bunch of labels here. Oops, that's not what I wanted. I'm going to put a bunch of labels here describing what they actually do. So this is reset pin 1. Do I want that pointing left? I think I want that pointing left. Yes, I do. Okay. So that's D0. All right. So which ones of these pins are mapped to which of the Arduino pins are not something I'm going to have memorized. So let me pull up Arduino Uno schematic. There we go. Hey, look, I've cache. Let's go take a look at this in my browser. Where is it? Nope. Yeah, that's what I want. Okay. So over here, these are the headers on the Arduino. This is a schematic for an Arduino Uno, which I'm basically copying. These are the headers on the Arduino itself. So there's they call them IO 0 through 7, but they're usually labeled D 0 through 7. And then like 8 and 9 and some others. Here are your analog digital or your analog pins. But this will tell us what they map to on the ATmega chip. So this is what I'm using as my reference for the labels that I'm going to be using on the schematic. This is the other one that they use as just a serial data through to a it's an actual microcontroller that they use for USB to serial conversion, and I've never fully understood why they put a full microcontroller there. But that full microcontroller has its own ICSP header. So there are actually 2 microcontrollers on your Arduino Uno, and you can, in theory, program them individually. I've never had an opportunity or a need to do that, but that's something that can be done. You'll also note that most of these pins are disconnected, so you don't get to do a whole lot with it. It's basically just USB on one side and serial on the other, so not a whole lot to do there, but you can if you want to. Okay, so go back to KiCad. Hi again. There we go. Okay. So pin 3, and I'm looking up at the Arduino Uno schematic. I literally just Googled Arduino Uno schematic, and that's the first entry that came up. So pin 2 was D0, and it's just straight down the line here. So D1, D2, D, D4, D5, D6, and D7. Okay. And then where does D8 start? This is where things get a little non-linear. Okay, so pin 14 and 15 are 8 and 9. So we're going to go up here. Oh, so maybe these are somewhat linear. 8, 9. Uh, that's right. These start sharing pins with the ICSP, which is also your SPI. It's kind of the same thing. ICSP is SPI. So, all right. So D10, D11, D12, D13. But not D14 because an Arduino does not have a D14. This is, in fact, XL1, XL2, Crystal 2. And then these are my analog pins. Are they numbered? They are numbered the same. Okay. So AD0, AD1, AD2, AD3, AD4, and AD5. We also have one random on the side of the chip. Don't know why. A ref. It's considered a power pin. All right, so I've labeled up my chip. Those are all the Arduino pins. Before I forget, let's go take care of this. Wire, move that out of the way. Rotate. Resonator, move that. Ground goes over there, and then I'm already doing that. So to the right, X1 over there, and X2. So you notice how I put a label up here of Crystal 1 and Crystal 2, and then I put the same label down here, Crystal 1 and Crystal 2. That is just a cleaner way of drawing a line from there down to there. It'll be the same node. Internally, it considers those two as having been connected. But I just don't like running wires all over the place. It makes it a pain in the ass to read. This was just so much easier. I can just look at this and say, oh, there's my crystal resonator, and those are the labels, and I know that they will be labeled to the right places. When you have a subsystem that makes sense altogether, like the battery and the diodes and the VN and the capacitors and all that stuff, that's fine to draw lines between. But when you're trying to get from a signal from one place to another, drawing a big old line across the page is just not the way I like to go about doing it. All right, so let's do that there. And I'm going to start drawing some right facing. And this pin 1 is reset. Okay, so these pin number 1 there is going to line up with pin 1 there, 2, 2, 3, 3, and so on and so forth. So I'm going to be recreating these labels on these pins so that they will line up when I put them immediately adjacent to each other on the circuit board. And E3 to 6, 4. So 1, 2, 3, 4, 5, 6. And then I jump over to 7 for VCC. Okay, so copy VCC on 7, and 8 is ground. All right. Then we'll go back to this. So 8, 9, starting at 9. Where's 9? 9 and 9, 9. Extel 1 and Extel 2. Okay. Extel 1 and Extel 2. Actually, let's drag that component ground, and dragging it will move the wires with it. Okay. Back to 11 is D5. Okay, so we'll pick up where we left off. D5, 6, D7, and D8. 13, and then 14 is up there. Okay, sure enough. And then 15 is actually going to be, let's do it this way so that they're oriented the same way. Okay, so I'm going to be counting down here as I'm counting up there. Okay, so 15 is 14, which is kind of annoying. 9, 10, 11, 12, 18, 19. So D13, 8, 16, 17, 18, 19, 20. Where's 20? 20 is over here. So another VCC. These are going to be backwards, aren't they? And then 21 is a ref. Hey, look at that. I can just copy that. Oops. I hit the right key. There. So what does it say? 15, 16, 17, 18, 19, 20, 21, 22 is ground. So we're going to copy that. Oh, this is getting crowded. I'll stretch this out. 22. And then starting at 23 right here. So A0, E1, E2, 83, 84, and 85. Okay. Let's drag all of that, give us a little bit more space. Move component VCC over there. Move that one, ground over there. These are kind of upside down, which is a bit of a bummer, but whatever. Okay. So now I've got my chip. I've got my header right on either side of it. You can get access to every single pin, whether you want it or not, because hopefully you won't be tapping into those crystal pins. That is everything-ish that I need to make this an Arduino. That is not entirely true. I want to get RTS and hook it up to a capacitor, a 0.1 microfarad capacitor. Okay, so I'm going to copy RTS, we'll call it there. And I'm going to copy that one because it's already facing the correct direction. And I'm going to copy that. And I'm going to rotate it. I'm going to stick it right there. And draw a pin from there to there, there to there. And look at that. Okay. So let me show you what I'm recreating here. This is a little bit non-obvious. Here we are. Okay, so here we are back at the Arduino schematic. Excuse me. This is the serial adapter, so it's USB on one side and serial out the other side. Hang on, trying to get it centered so we can actually see it. So here are the serials coming out of the out of that Arduino over here into the serial of the primary Arduino. This is the one that's actually hooked up to all the headers and everything. And we got some LEDs that do activity. But here's the other thing that comes over, and it's just a digital output. It has a jumper there that can tie it to ground. I'm not entirely sure what that does. That makes it so that you don't actually reset, apparently. But then it's labeled DTR, and that's basically just a one of the flow control lines coming out of your serial port that software can access. It can signal and say, "Hey, data terminal ready. I am a data terminal. I am ready. Go ahead and send me data," or clear to send or request to send or whatever. So it's a digital control line. That's hardware flow control. We don't actually need the flow control because the CPU can handle the full speed on the serial line, so there's no flow control necessary. But we still have that pin, and we can use that pin to trigger a reset on the main CPU because we need to reset the CPU. We need to reset the microcontroller to get it back into its bootloader, and the bootloader sits there for some number of seconds or microseconds or milliseconds and waits for some sort of a sign on the serial port to say, hey, I'm trying to load some new software on you. And then after that timer expires, it loads your main program. But that means that the serial cable, the programming cable, needs to be able to reset the CPU. And so this digital line comes out here and goes through a capacitor, a 100 nanofarad, which is the same thing as a 0.1 microfarad capacitor. And then you'll notice that that gets tied to the reset line. So I'm going to do the same thing. That's exactly what I'm recreating over here. So back over to Eagle, not Eagle. Nope, wrong one. Just kidding. That one. So that's what I'm doing over here. So the RTF's coming from pin 6 on the FTDI header. I'll be perfectly honest with you. It might be the CTS. I can't remember. I'll have to go find. Let me try, because we did this on the darknet. Darknet badge schematic. Google known stuff. DEFCON.org. What? What is this? Hey. This looks interesting. What is this? What? This is not my project. Somebody else is doing something awesome. What is this? DCGdark.net? This is news. Huh. Interesting. Okay. That is not what I was looking for. Unofficial badges. That's what I want. Let's see if it's got a PDF in here. Schematic board. I do not see any PDFs. Really? Hey. That's me. Hi. Building and burning, preparation, burning chips, automated and build bomb and assembly. Yeah. Yeah, by the way, if you want to make your own DEF CON Darknet badge, look at this URL, github.com/thedarknet/HHVKIT, Hardware Hacking Village Kit. That is the GitHub repo you want to go to. Hardware libraries, software, readme, be hardware, but these are just all the Eagle files. None of these are a PDF. And right, I'm going to have to load up Eagle. Oh, variants. Because Crux is kind of a jerk. And by kind of a jerk, I just mean devious. He's actually really awesome. Okay. Why did that pop? That is not what I wanted. That is really not what I wanted. Can I just download? Where's the... I'm logged in. Why can't I just download? Really? You gonna bust my balls like this? Download zip. I don't need the whole zip, but whatever. All right. I'm gonna stop screen sharing that. I'm gonna let you look at my ugly mug for a while I go figure this out. Move HV kit to source. Maker HV kit. Move HHV kit. Dot dash. Oh, interesting. Apparently, I already have it checked out, but I don't know if that's the same version. So HHV kit, unzip, all that, and .ch. Hey, look, there's Eagle. Oh my God, your Eagle's out of date. Yeah, I know. It's been a while since I've used Eagle. Hey, knock that off. Come on. Okay. So here is the schematic for the darknet badge. You'll notice very similar. I've got power in from our ICSP header and from our FTDI header. Yep, DTR. So it was pin 6. I got it right. Pin 6 goes through a 0.1 over here to reset. But we got a couple of diodes. It's actually a single component on this badge that goes to the +3 volt. We're also doing software bit banging USB on this badge that I'm not going to be doing on the badge that I'm building right now. So yeah, but here you can see this is the simplicity of the darknet badge that we made this year. Pretty cool. You can go download all of this and build them yourself. You just download the .brd file from that URL I listed earlier, send that off to Osh Park, and you can get your own made. Maybe make some modifications to it before you get that sent out. That's what you want. But all I needed to see was this DTR through a 0.1, pin 6 through a 0.1 over to reset. That's what I needed to know. It's pin 6. Bye-bye. So we'll go back over here and RTS. Okay, so it's labeled something different, but it's the same thing. All right. So we are doing pretty good. Let's put a diode on here somewhere. And by diode, I mean LED. LED. Look, an LED. We're going to need a resistor on top of that. Got a device, R small. Yoink. And yeah, just the one. Oh, that goes to, actually, let me just copy that ground to there. And then I'll need to feed this from a pin. Now, a little bit about infrared. Turn this off here. A little bit about infrared. The way infrared remote controls work is they do not actually just take the infrared LED and turn it on for a 1 and then turn it off for a 0. It's not just baseband serial, right? It's not like the same serial that you would use out of like pin 0 and pin 1 on this Arduino here. The reason you don't do that is because the infrared light spectrum can be very noisy. And so what you actually want to do to get rid of that noise is you want to modulate your serial data on top of a 38 kilohertz signal. And bringing it up to about 38 kilohertz is the standard. You can do whatever frequency you want, but the receivers are ready-made for 38 kilohertz, so that's what we're doing here. by modulating it at 38 kilohertz, the receiver gets to filter out this higher frequency that doesn't normally get, you don't normally get a lot of noise in the infrared spectrum at 38 kilohertz. So by modulating it up to 38 kilohertz and then filtering just for that 38 kilohertz carrier, you can tell whether what you're receiving is noise, just ambient noise, or whether it's actually data being sent from the other side. So we need to modulate our IR at 38 kilohertz. So a 1 is a whole bunch of 38 kilohertz pulses, and then a 0 is silence. Rather than just being a 1 being bright infrared, and then a 0 being being darkness. So we got this 38 kilohertz infrared flashing for a 1, and then darkness for a 0. So we need to be able to modulate our 38 kilohertz, or modulate our LED at 38 kilohertz. And I could just bang that by writing a loop around it, but it's a lot easier to use one of the onboard timers and pulse width modulator, or the output compare registers on one of the built-in timers. And all of the built-in timer output compares are the PWM outputs. So basically what I'm doing is I'm trying to make sure that I have access to that I put this infrared LED on a PWM pin so that I can use the built-in hardware to do the 38 kilohertz modulation. It'll be a heck of a lot easier in the software. So the first of the PWM pins is, I think, D3, if I remember correctly. Yes, OC2B. So that's output compare from timer 2. The second, the B comparator, which is the second comparator of the output of the third timer, which is 0, 1, and 2, and it's the output compare. So D3 is the one I want to put there. And, oh, you did not see any of what I just said, so let me go back over there. Try that again. D3, OC2B is one of the functions that this pin can have. It can also have pin change interrupt number or external interrupt int1, or it can just be standard a GPIO pin, or in the case that we're going to use it, OC2B is the output compare for timer number 2, which is actually the third timer, and it is the second output comparator, the B comparator, as opposed to the A. So you also see like an OC0B, OC0A, so on and so forth. So those are all the PWM pins on this thing. But you don't care. What we really care about is that I'm going to make this D3, yoink, and there we go. There is our LED. I'm going to change the value of the to IR and move it over there. This, let's see here. At 4.5 volts, probably a 2-point-some volt drop across there. So we're going to have about a 2-volt drop across the resistor, and I want it to maybe push 5 milliamps. If I put a 1K across the 2 volts, that's going to be 2 milliamps. So to double that, make it a 470. Okay, so I'm going to put 470 ohms there. Rough math. Doesn't really matter. It's not all that critical. The lower the number I put there, the less resistance there is, the more current will flow through that transmitter, and the brighter it'll be. But it also means that the more current it'll consume, and the shorter your batteries will last. Although this is only going to last for about 3 days, and it's going to be on a 3 AAA battery, so it'll have plenty of current. But 470 will be plenty bright. We'll be good. Okay, then I need an IR receiver. And this is where I have already made one, so I need to go to my Smitty library. 38 kilohertz IR receiver. There it is. Look at that. Yeah, where am I going to put the receiver input? I don't know. D2? D2 sounds good. We'll put that there. D2 is not a PWM, so I'm not going to want to use it for an output somewhere. It's not 0 or 1, which is your serial ports, so I kind of don't want to use those because I want to be able to use them as a serial port. Yeah, that seems reasonable. Okay, so I'm going to copy that bad boy there and that one over there. Okay. Yoink, and Yoink. Okay. So what do we got? We have our chip. We have our headers. We've got our infrared LED and receiver. We've got our battery pack and our power mixers. We've got some bypass filtering caps. I think one of those is going to go right next to that. I've got my reset controller for the serial port. I've got the serial port header. I've got the ICSP header. I've got my crystal oscillator. I think the one other thing that I wanted to put on here was some WS2812, the NeoPixel LEDs, the individually addressable, serially connected LEDs. I don't think I currently have any 2812. No, I don't. I don't have any packages for this. So we get to go over how to make a package. That'll be neat. All right. Library editor. Let me switch what screen I'm sharing. Hello again. That one. All right. So this is how we make a new component in KiCad. This is the library editor. And I'm going to select which library I'm using. And again, I'm really sorry that you can't see the modals. KiCad uses a lot of modals. So I just told it to select my Smitty lib, which is my library that I use of all of my own components. Select working library. Let's see here. Library browser. Create a new component. That's what I want to do. Component name, WS2812. Reference designator, LED. One. Component with alternate body style. Nope. Create component as power. Nope. Units are not interchangeable. Nope. Show pin number. Show pin name. Huh. So I got to figure out how I'm going to do this. Well, let's just go with the defaults for now. So what are we going to make this thing look like? Well, it's going to be a package. Yoink. Oh. My dog's nosing at things. There we go. Let's drop a few pins on this thing. Pin name VIN. Let's do 5 volt. Number. I don't know. I don't think there are any standards for this. Shush you. Oh, that's what I'm doing. So, sorry, I'm going to be boring for a little bit. I bought some components from eBay, but I don't want you to see my eBay, so I'm not going to share that screen. Oh, great gravy. Bought these a long time ago. Stand by. Standing by. Firing in 3, 2, 1. There they are. Okay. What is the pin out of these? Package type D in, VDD, ground, and D out. Okay. So for here, let me go ahead and share this now that. Come on. Stupid tooltips. Where are we? There we go. All right. So these are the components that that I want to put on here. So they're 4-pin 10mm LEDs. They're big LEDs and they've got 4 pins on them. And it's not a ground red, green, and blue. They have the APA 106, which is the same thing as the WS2812. They use the NeoPixel library that Adafruit has put together. They run off of 5 volts, and it is a data in on one pin and then a data out on another pin. Look them up. They're actually really neat. The idea, oh, excuse me, they're 8 millimeters, not 5s. The idea of how they work, that you send it just a stream of bytes, and the first 3 bytes get consumed by the first LED. Whenever an LED sees silence for a while and then data coming in, it takes the first 3 bytes that it sees on that line and uses it as the red, green, and blue value for that particular LED, and then it consumes those and does not pass those on. But all of the data bytes that come in immediately after it, without a pause, it just sends right on through to its data out. And then the second LED on the string gets the second set of 3 bytes, but to it is the first set of 3 bytes. So it consumes those 3 and passes everything on through it. So in this way, you can string as many of these as you want together, and they all will just get however much data you send down the line. And you don't really need to be able to address them. You just send data in the proper order, and they all get the right data. It's kind of neat. So in this particular case, what I'm going to do is I'm going to put 2 of these on the board just so that you have enough to play with. And then I'm going to put a header next to them that will take the data out of the second of the 2 LEDs and put it into a header so that you can hook up a string of more LEDs if you want, like either like one of the strips or Christmas lights, or they make little sticks of them, whatever. So yeah, it's going to be neat. But in any case, we are going to go back to parts editor. That's what we want. Okay. So pin number 1 is going to be D in, and it is going to be a right facing. We're going to do, let's see here. That's kind of a long thing. Okay. Pin name is going to be pin number 2. And ground pin 3, and there the out pin 4. All right, move that there. And then, because we like graphics, let's draw some LEDs. Copy block. Crap. Copy and paste in KiCad is kind of questionable. Wait, where's the point? There's no paste? Seriously? Oy, okay. Well, we'll do it the old-fashioned way. We'll draw it. That sound you hear behind me is my dog walking in and out of the dog door. 1, 2, 3, and then we'll put 1 there. And these are only RGB LEDs, so I will not draw more than 3. Oh, but I do need to draw the obligatory. Oop. They're not LEDs unless you make the little lightning bolt. Okay. Let's center this a little bit better. How's that look? Does that look good? That looks good. I think it looks good. Okay. So I'm going to save the current library. Include last component changes. Yes. Yes, I would like to update smitty.lib. Okay. So I now have a component. Actually, you know what? First off, let's move that there. So the anchor point's always at the origin, and you want, whenever you pick up a component or move it, it's always going to move directly so that the anchor point is underneath your cursor. And so I find it's usually easier to have that be on a pin. And pin 1 is arbitrary, but it gets the job done. Okay. So let's go back to here. And I'm going to, I don't know whether I have to reload it or not. Again, KiCad could do better on some things. Oh, nope, there it is. Sweet. Okay. So there's one LED, and we're going to copy that down to another LED. And we're going to copy some ground over here. We're going to copy some VCC over here. And I'm going to, again, pick a random arbitrary digital I/O pin, preferably not a PWM in case people want to use PWMs for something else. So let's go with D4. And we'll do right facing, we'll do D4. And then VDD, VCC is the same thing. One's for TTL, one is for FET logic, or one's for BJT, one's for FET logic. But they both mean positive voltage. And then my D out there, let's do it this way. And then let's give me a 3-pin header. Give me a connector, just a standard 3-pin header, 1x3. Yoink. And let me see what pin out my ground, then data in, then VCC. So we'll do VCC first, then data in, then ground. Okay. So we'll just do all of this. So that's VCC. Oop, hey, how about we move you down there? And do that, and then that. There we go. So there are our LEDs. I'm going to have a data out pin come from the microcontroller, and it's going to go into the first LED, out from the first LED to the end of the second LED, and then out from the second LED into the pin header. And let's set the value on this, WS2812 LEDs. Move, rotate, so it's a little easier to see. And okay. I think that's all I'm going to put on this badge. Though I do want to have more capacitance by here because those LEDs consume a fair bit of power and will put some pretty bad noise on the line. Do I want to make a CAN capacitor here and put like 100 microfarad on it? Yeah, that's probably the right way to do it. So we'll come over here. Device, we'll do capacitor polarized. Oops. Value 100 microfarad from booty. But we're going to put that right by the light connector. And I think that's it. Did I miss anything? I don't know why I'm asking you. Nobody's actually in the Hangout. But I think that's all I need on the schematic, at least. Let me save that. Yeah, that's all I want to do. Nope, I lied. That is something I did want to add. Okay. I'm going to add a outline for an unpopulated component. Wait, I do have it on there. Sweet. We'll do that. Okay. And as usual, we're going to copy some power pins around. Put that one there. Copy that one. Put that one there. And then We're going to hook up an I2C bus to this thing. Oh, and I want to put an I2C header on it too, so that people can get to I2C easily. Oh, that's right. Okay, so if I remember, I2C is on D5 and D4, or 85 and 84. Yep, 85 is system clock. So 85, make that left pointing. There we go. Which means system data is going to be 84. So left pointing, and everything else is a no connect. So this chip, ATECC508A, I encourage you to do some research on this. It is a little crypto chip made by Atmel. It is neat. It does elliptic curve crypto in hardware. It does SHA-256 in hardware. It does ECDSA. It does all kinds of things, all in hardware. It's got a little hardware random number generator that is pretty good. It's got some real good entropy, very fast, very useful little chip. I wanted to use these on the darknet badges, and we may still use them this coming year if I can get off my arse and figure out how to program it properly. In the darknet badge, we are doing a crypto exchange across the infrared. It's using TEA, tiny encryption algorithm, right now, and TEA is broken. It is known to be broken. I intentionally used it because it was broken, because I wanted people to be able to hack the crypto, and I'm realizing now that we're doing more with these things than I want to be hackable. So I want to upgrade to stronger crypto. The other problem with TEA is that it's symmetric crypto, so we need to have we need to know what the private key is on each of those badges. I would prefer to use public key crypto, where the badge can generate its own public-private key pair, keep the private key private on the badge, and then just give me the public key. It's a much safer way of doing this kind of thing. But without ECC, public key crypto is, 1024 bits, or 248 or 2048 bits, or 4096 bits, right? I mean, you got bloody huge keys to get some level of security. And originally, when I designed these things, they were just using LEDs blinking Morse code to be able to communicate to the user, to be able to tell the user what to send to the daemon, which is running this whole game. And it ended up being, trying to blink out a 200 or a 2048-bit public key in Morse code and having the user copy that was just insane. I ended up actually cutting the TEA algorithm in half to make it even smaller. So it ended up being like 15 or 16 or 16 characters, or maybe 8 characters in Morse code that the players had to copy, as opposed to an entire RSA key block, right? That's just stupid. I'm not going to do that. But with ECC, well, a combination between the fact that we're switching to using USB. So the USB ports on these badges, they look like a USB keyboard. You plug them into a computer, you hit the USB button, it shows up as a keyboard. It, quote unquote, types a bunch of things, types all the data that you used to have to copy with Morse code, and then disconnects as a keyboard. And so that allows us to send larger blocks of data. But I still want to keep them small if I can. So I want to use ECC. I want to use elliptic curve crypto, where 256-bit key has roughly, I think it's 128 bits of security. I think it's about half, as opposed to get 128 bits of security, you need like a 2048 or maybe a 3072 byte key or bit key for RSA. The sizes are just redonkulously large on RSA. I think it's 10 times or more compared to ECC. So I wanted to use the smaller keys. But the other problem is, to generate your own key on the badge, you need to have a good source of entropy. And I was looking at building a hardware random number generator out of discrete components, which would be a lot of fun. And I would love to do that. I would love to be able to explain to people, look, here's how a random number generator works. You generate a high voltage, you reverse bias this diode or this transistor, and you amplify the output, and all the thermal noise across that reverse bias junction gets amplified, and you turn that into ones and zeros, and then you have to process it and stuff like that. And so I was looking into doing that and using that to generate keys, but that ended up being kind of more of a pain in the butt, and that still didn't get me the ability to do elliptic curve crypto, other than writing it in software, and writing it in software on a system with what is it, 2K of RAM and 2K of RAM and 32K of flash, it was going to be problematic. So doing it all in hardware was a really nice option. So when I found these chips from Atmel, the AT-ECC 508A, I kind of got very excited because it solved both the public key problem and the random number generation problem. The only problem is that they only come in surface mount. They do not come in through-hole components. And I was trying to keep all of our Learn to Solder kits entirely through-hole and not do any surface mount. So that's really that. And well, okay, there are three things that are preventing me from saying we're definitely doing this. One is that it's surface mount. Two is that I'm still not entirely clear that I've got a working library for it. Let me rephrase. I know I don't have a working library for it. But I'm working on that. The libraries that are out there don't play nice with Arduino. They don't play nice with the wire library, which we're already using for some other things. They kind of take the I2C hardware by the brainstem and assume that they are the only thing talking on I2C, or that you are also taking I2C by the brainstem. It doesn't really play nice with the wire library. So I was trying to modify some of the Atmel 508 libraries to work with wire. And I haven't gotten that working yet. The third problem is that technically I signed an NDA to get the spec sheet or the data sheet for the 508. So the programming interface, the API for the 508 is covered under NDA. So I'm not sure I'll be able to share my source code. And I'm not going to put something out of the DEF CON darknet with source code that I can't share. So that may be a roadblock or a showstopper. I don't know. I sent an email to Atmel and never got a reply, and I haven't followed up. So I need to go contact Atmel and confirm whether the NDA that I signed means that I cannot share my code. By default, I assume it does mean that I cannot share my code. So really, it boils down to me trying to get approval to open source any code that I write against the 508 and against the library for it. Because you can get the libraries, they're just not ones that play nice with Arduino. So I kind of want to enhance that library, make it play nice with Arduino, and then release that. But I'm under NDA, so I don't know if I can. So it's kind of broken in my opinion. But that's where we are with that. So in any case, on this board, I'm not actually planning on using an ECC 508, but I kind of want to put the footprint there and just leave it unpopulated and let people, if they are interested in it, because I'm going to be doing this at a security conference that my employer is running, private security conference. And so there are going to be a bunch of security nerds there and a bunch of crypto nerds there. And so I want to give them the option of putting their own chip on there and doing their own thing with it, because I think that'd be fun. So I'm just going to leave an unpopulated surface mount outline on the board for that. Oh, and I wanted to put an I2C header on here somewhere as well. So I'm going to go to con, my connectors, and just get a 1x4 header. Okay, and yoink, and as usual, you know what? There is somewhat of a standard on this one that I want to stick with. Stand by. Am I? Maybe. Hang on, I'll be right back. Hey, look, I'm back. That is a very cheap circuit board that you can buy on eBay that has a DS3231. It is a real-time clock chip. It's got an I2C bus on both sides. That's the same bus. I think it's an in and an out, but they're just parallel, so it doesn't really matter. It's got a little coin cell battery on the back to keep its time. I just pulled this one off my Raspberry Pi home router because it only uses it at startup and shutdown, so I can pull it off. But that pinout right there for an I2C bus is actually pretty standard, so I'm going to copy that pinout right there. I don't know what people are going to do with I2C on this thing, but if someone comes up with an idea, I want to enable it. So pin 1 here. Nope, wrong tool. Go over there. Pin 1 is going to be SCL. SCL is 85, and I want that to be right facing. And then SDA, which is going to be 84. Put that there. And then CC and ground. Give me some space. Okay. And copy to there, and copy that one to there. Okay. All right. Set the value of that I squared C. Okay. Rotate it like that. All right, ladies and gentlemen, I think that is everything I wanted to do on this schematic. Yeah. All right. So the next thing we do, there's a tool up here called CVPCB. I have no idea what the heck that stands for. Oh, it's going to make me annotate. Okay, that's fine. Yep, go ahead and annotate. Now, KiCad is kind of neat because you don't have to go in and hang on, I'm reading something else. Following errors occurred while attempting to convert the footprints. IC1 footprint DIL 28 was not fine. Yeah, that's fine. Shut up. Okay. Get back here. Okay. So you'll note that I never actually assigned component names to these: LED1, LED2, D1, D2, so on and so forth. There is a process by which you go through in KiCad to auto annotate things. I went up here and chose to run the tool that associates. Let me share the window so you can see it. There we go. So it associates all of these are all of the components that I have on the board. You can see the battery and all the capacitors and yada, yada, yada. And then these are all of the hardware, the physical outlines that it knows about. And this is how you associate this component on the board with this particular outline. So for example, this one is in libraries. Unfortunately, I didn't know better, and I call this one libraries as opposed to Smitty. That one should be named Smitty, but whatever. What are you going to do? So here is a custom component that I made that is a 3x AAA battery holder. There is a way to view things, but it, of course, pops up in another window, which means that you can't see it when I've got the screen share on. So footprint viewer. I'm going to bring up the footprint viewer, and you can see that this is a 3x AAA battery holder. I don't have a whole lot of graphics, so it's not all that exciting. But as I go to the capacitors, you will see all the different capacitors. I'm going to do through hole. These are all the different outlines for the different types of capacitors. Now, for the 0.1 microfarad disc capacitors, this is the one I'm going to want. So it's a 2.5 millimeter spacing between each of these pins. Basically, it's a 0.1 inch, 100 mil inch spacing disc capacitor. And so those are the ones that I want. But you can see how that's these are all the different component outlines. So that's what the outline viewer looks like. Unfortunately, I can't show you the outline viewer while I am showing you the other thing where we actually perform the mapping. So we're going to go back to the mapping. Pretend that you're looking at the outline viewer as well. So I've selected all the 0.1s, and I'm going to make them all that outline. Now the 100 microfarad, that one's going to be a little bit different. I'm going to want to use of these radials. I'm going to give myself some space. I think I still want a 2.5 millimeter pin spacing. The length doesn't matter. I don't know why they even bother putting that there because that doesn't show up. But the 6.3 millimeter diameter will give us, it's like the small electrolytic capacitors are 5 millimeters in diameter. That's kind of a medium size. And then the next one up is the 7.5. I'm going to stick with the 6.3. Then I'm probably going to end up using a 5 millimeter can instead of a 6.3 millimeter can, but I'd rather give myself more space and not need it. So we'll do that. And diodes. Okay, so diodes through hole. I think 40. Yeah, so the DO41 is the package that I have for these diodes. And horizontal, meaning it's, splayed out over, 10 millimeters here, which means, what is that, 0.4 inches? Hang on, I'm looking at the thing right now. 0.1, 2, 3, 4. Yeah. So roughly the spacing of the pins on a chip. No, it's actually a little wider than that. Anyway, so that's the diode that I want. Now IR, this is going to be a standard LED. So we come over here and we'll just do a standard 5 millimeter LED. And it complained that it doesn't know what a DIL 28 is, and that's fine. We're going to come over to sockets. Nope, just kidding, not sockets. Where is it? Diodes, display drivers. There's no dip. Oh, housing, dip. There we go. That's what I'm looking for. It's going to be 28 pin. 28. Or do I want long pads? Let's do long pads. I'm going to go back over and show you the component viewer again. So that is the normal pads for the 28 pin dip, and those are the long pads. I think we're going to go for the long pads. They're a little easier to solder for new people who are just learning how to solder. So we're going to go back to that. Okay, now I don't know that I have any 4-pin LEDs. Maybe 5 millimeter common cathode. That might do it. I'm going to go with that one. So, and again, flipping back and forth between windows, apologies. That looks like my LED, although I got the 8 millimeter, so it's going to be a little bit bigger than that. But as long as I give myself some space, it should be fine. I could go in and copy this component and give it a bigger circle, but let's be honest, I'm lazy. I'm not gonna. So yeah. There. Okay. Okay, so now I need pin headers. There we go. And I want a 2x3, not angled. Nope, straight. 2x3. There we go. Straight up and down. Oh, I never actually changed the name. Whoops. Okay. That's going to be a 1x6. That is for the FTDI serial header. I squared C is a 1x4 header. And connect 1x4. Oh, 14. Oh, those are the chip things. We'll go there and put another one there. WSAD. That is a 3x, if I remember correctly. Yeah, power, data in, and ground. Yep, okay. And that's a resistor. So let's go to my resistors. Resistor through hole. I want not an array. Resistor horizontal 10 millimeter. Okay. ATECC 508 is an SOIC 8 SMDB packages. SOIC 8. Nope, not the N. Not the power pack. What? Oh. Maybe it is that one. What is N? I don't want the power pack. especially since that looks to overlap a bunch of pins. Oh, N is in normal or narrow as opposed to W for wide. Okay, so no, that still doesn't look right. I don't trust that one. Let me see if I can find another. No, they've been changing their libraries around. I think this is SOIC. There we go. SOIC 8. Pitch 1.27. No, it's not that small. Oh, wait, maybe it is. If that's 2.5, 1.27 is half of a 0.1. Yeah, that's right. Okay, we'll do that one. And then the receiver. I think I've made one of these outlines as well. Nope. That's it. Yep, it's that one. Okay, and the ceramic resonator. Crystals. You can tell I've done this a fair bit. Resonator, nope. This is a 3-pin. It is. A little bigger than I need, but it gets the job done and the pinouts in the right order. So, yeah, that. All right. So I have now gone through all of my components and mapped them to physical outlines. I'm going to save that. And then I am going to go back to the circuit board, and I need to generate a netlist. I'm going to generate a netlist. I'm going to call it by the same name, and it's going to save that. So now I have a netlist. Now I should be able to run PCB new to layout printed circuit board. All right. Let's change our windows yet again. PCB new. Okay. So here's my PCB program, and I'm going to load a netlist. I'm going to read the current netlist and close. Hey, look, all my components. And it plops them all right on top of each other, which is rather annoying. That's what we're going to do. So I'm going to move my battery out of the move my battery out of the chip out of the way, move these there, right there. I have to unbury everything, which is kind of annoying, but it's the way this stuff works. That's a diode. I'm going to put that up there. That's another diode. I'm going to put that one there. That is, oh, resistor for an LED. Footprint C1. Oh, that's my reset capacitor. Okay. Footprint C2. That one's going by. I'll go by the LEDs once I get it out there. Don't remember which one. Oh, that's the LEDs. Okay, good. So that goes there. Oh, that's another capacitor. Each of the footprint U1. All right, what's U1? Oh, hey, look. That's that. We're going to put that somewhere. I don't know where. Footprint C4. And I'll put that there. C5. Where do I want that one? I want that one by, oh, it's going to go down there because that's going to go by the IR receiver. Footprint D3. That is my LED, so that's going to go there. LED 1. That's my 2812. LED 2. That's my other 2812. There's my resonator, which is going to come down here with that capacitor. Or not my resonator, the receiver. That's my resonator. And that's going to go right there. Okay. All right. So those are the components of my board. Oh, if I remember correctly, this is all much better oriented if we uh, uh all right. Thank you, Packhead. Um, uh, over here, move, over here, move, there, and then move that one, magically everything works again. What? There we go. And you go right there. Okay. All right. So you can tell that I've laid some of this out awfully quickly because I have some experience. I've done these things a few times. Where? Why are you not showing me a rat's nest for the data lines? That worries me a little bit. Okay. Um, okay. Where do I want all of this to go? I think I want these guys up at the top. So here is a neat trick that I learned. I arbitrarily chose which data pins to run these to, but strictly speaking, it is arbitrary. I can just easily move those pins. And to the degree that it makes it easier to route things, I still can. Um, so, for example, this data in pin comes all the way down here to D4. You probably can't see that. So that's D4. That's where we chose the data out for the 2812s. So I could run a line all the way up there, or I could just grab D8 or D9, one of the ones that are right next to it, and just go yoink straight up in there. And as long as I'm not using those pins for anything else, which right now I'm not because this Arduino is horribly underutilized, um, then you can grab any pin you want. And so we could just go back to the schematic later and update it to suit our needs. Um, so I kind of want. Let's move that up there. No, because that. Okay. I do kind of want that right there. And then there is an I squared C bus connector, that one. And we're going to go. That. Like that. And then I got to find out where this infrared stuff is going to go. Let's move that one. Where's your pin 1 and pin 2? Why do you not show any connections? All right. I think my netlist is broken. I would expect. Oh, I'm an idiot. Haha. Um, I never actually connected these up. These are still labeled Mosi and Miso instead of D whatever. So let's patch those together. Do I want to just replace these with the D's? No, I kind of want to keep those labels there. Okay. So let's create some patches. Where do I want these? I'll put them up here. Okay. So Mosi, CK. All right, and then here, left facing Miso is on the chip somewhere. Miso is D12. There it is. D12. And Mosi, so Miso right there is D12. So Mosi is D11. D11 and clock. System slab. There it is. So D13. D13. Okay. So that puts together my SPI bus. Now I need to do something similar for I squared C. Or actually, I don't need to, but I'm going to do something similar for I squared C. Oh, also my serial. Okay. So, hey, knock it off. 0. Line 1, receive line, I don't remember. Doesn't matter. And then I'm going to do FTX and FRX. And I don't remember. So that is the D0 is the receive line. And I want my FTDI transmit to go to my D0 receive. Okay, so 50-50, I won. Okay. Now let's do the same thing with I squared C. Let's make this a little bit easier to understand for the I squared C bus. So instead of doing 85 and 84, I'm going to move that up there. And 84. Delete. What did I say? SCL, but it's a different SCL than the SPI bus. So I got to be careful. I don't want to tie those together. So that's SCK, and I'm going to make this SCL. Okay. SCL and SCA. Okay. And left facing SCL, SCL, and SCA. Okay. Well, that is more clear that that's I squared C. Oh, while I'm here. VFTDI. Okay. And that is left facing already. SCL and SDA. And I get in the right order. AC. Nope. Lost this one. Easy enough to fix. So 84 is SDA. Okay, that's right. And 85 is SCL. Okay. So connect all those together. All right. So all of my serial buses, my ICSP, my FTDI serial, async serial, and my I squared C. So I've got all the serial buses exposed. SPI and UART and I squared C. They're all on headers. Pretty cool. And I've got all labeled. Okay, so I'm going to do that. I'm going to save my changes. Then I'm going to generate a new netlist. We do not need to go back to the mapper that maps components. That has not changed, but we do need to save a new netlist. And then go over Excuse me. Go to PCB, and then we need to load the netlist. There we go. More rat's nest just showed up. That's good. Oops. ICSP header likes to be up here more. I can handle that. It's raining outside. I'm in California. That's novel. So this is the part of circuit board layout that's kind of a pain in the butt because it's more art than science. And I can't really give you a straight thought process like I do when I'm doing board layout or schematic layout. Because it's something that changes. Yeah, I don't know what's there. Move it there, and I'm gonna move. Oh, I'm gonna keep the serial over there. We'll go ahead and put those. Since I need to pull that from over there around and from there around, so it's not going to matter. Okay. I really don't like having that over there. All by its lonies. All right, you're moving. Hey. All right. All right, let me get some board outlines in here. We still don't have a board outline. Okay, so board outlines, we go select edge cuts. That's what I want. Okay. Stand by for a quick second. I'm going to check up on the Twitters. If anyone's trying to talk to me. Oh, 7 notifications. Oh, people are saying they can't get into my Hangout. Oh, George, I'm sorry. Well, that's unfortunate. I'll have to figure this crap out at some point. All right. Well, not going to figure it out right now, unfortunately. It's a little late. I'm probably going to be wrapping up pretty soon here anyway. All right. Board outline. What are we going to do? Well, I'm going to use that tool. I'm on edge cuts and just do kind of a swag. I want some above my battery connector or my battery holder and probably some below my battery holder too. But roughly the width of the battery holder is probably not a bad idea. I think. And then, where is it? Right about there. And then we can adjust this. But unfortunately, doing that. Oh, too far. How big is this? Where am I? 3.9 and 5 point, call it 5. So nope, I did that wrong. 2.7. So 3.9 and 2.7. 3.9 to 5.4. So that's, what is that, 1.5? 2.7 to 5.5. It's what, 2.25, 1.5 by 2.25. So that's pretty small. That'll be pretty cheap to fab, and I could fit everything on that pretty easily. All right. Oh, haha. We need to reverse that. No, cancel footprint. Flip. There we go. Oh, one on the back of the board. That's all. You on the back of the board. Well, dagnabbit. Does that work? I don't know if that'll. Having a little section of board cut there. I don't know. Okay. And this is where I wish I had a portrait screen. So the battery's on the back. Back silk. There we go. All right, made the battery go away. Oh, but I don't want it there because that's where the pins go. Well, that's unfortunate. Okay, so I don't want my pins right on top of the chip. But I don't want it at the very top either, because this is going to be a badge. Let's make a hole. No, that's not a fiducial. What am I doing? There's a way to plop a via or a show path outline. I'm really just making this stuff up as I go. There is a way. Is it add footprint? I didn't think it was. There's a way to just drop a hole on here somewhere. Crumb. I am totally blanking on this right now. Mounting hole. There we go. 2.5 mil. 2.7, 3.5. Oh. Do I want a 3 millimeter? That's a little small. Let's go with a 5 millimeter hole. Oh, that's kind of big. I don't know that that is what I want. Mounting hole. Oh, there's my hole, and that's just a keep out zone. What layer is that on? What in the CMTS user? I don't even know what that is. Okay, not what I want. You know what? I think my brain is starting to shut down. I am going to call it a night. I think I've been going for about 2 hours anyway, so that's probably enough. it's probably enough of a YouTube stream for keeping people into trouble or out of trouble or who knows what. Anyway, thank you for joining me. This has been Smitty is working on something. Tonight's something was a learn to solder kit for a hardware hacking village that I'm going to be running at a work security event at the end of March. It's going to be a little Arduino compatible microcontroller. It's got various different serial buses that you can use for things like an ICSP header to program it, an FTDI serial header that once you put a Arduino bootloader on it, you'll be able to program it through the serial header, or you can just use it to get data in and out of it if you want a console for whatever you're doing. It's going to have an infrared transmitter and receiver. It's got a couple of RGB LEDs that are individually addressable, the WS2812s. Battery pack, onboard crystal. It's going to have an unpopulated header for an ATECC 508A, which is a cryptography chip. Yeah, and I think it'll be, a neat little project for people to learn how to do some soldering. I might throw some other LEDs on the PWM pins on there. One thing that the Darknet badge did is it put some holes in the solder mask and the copper mask with some letters on them, and then put surface mount LED components on the backside facing through the board so that the board kind of lit up, which is something that I really like. So I might try doing some crazy board outline stuff like that. Crux did a really good job on those. So, but yeah, that's what I've been doing tonight. I'll pick this up again. I don't know when. Maybe tomorrow night. I don't know. I don't really know what's going on this weekend, but next time I start working on this, I'll do another one of these. Anyway, thanks again for joining me, and we'll catch you next time.